Okay, welcome back. So today I'll be talking about the resonance tube. So resonance tube is a simple instrument that we use to measure the lengths, the wavelengths, the frequencies, the sound of air, and those relationships using the concept of resonance. And the resonance tube also uses the concept that you learned in stationary waves. Those are the antinodes, nodes, and the other stuff you have to take in the wavelength, the length of the tube, and so on. So resonance tube is just a practical example of using the stationary waves in closed and open pipes. Alright. So to begin with, let me introduce what is meant by resonance. To introduce you about the concept of resonance, I will take a simple example in which I will take a tuning fork and a piano. I will keep these two instruments together. Together means in close to each other. And first of all, I will vibrate the tuning fork by hitting it on some surface, and then I will actually vibrate the air column using the piano by playing some notes on the piano. At some instance, the frequency emitted or the frequency distributed to the nearby air column by the tuning fork will be equal to that by the piano. So at that occasion, since the natural frequency of the tuning fork or the piano is equal to the surrounding air column, the frequency of the surrounding air column as created by either the piano or the tuning fork, we call that phenomenon the resonance. So resonance occurs when two frequencies which are in closed contact is in same vibrating with the same frequency. Alright. So to begin with this experiment, let me introduce about the resonance tube. So resonance tube, as you studied in the case of waves, can be considered both as an open-ended or a closed-ended tube. It's a very small tube of very small diameter, and it is used to examine the characteristics and resonant lengths to different frequencies of the closed and the open-end tubes. So you know about the characteristics about the stationary waveforms, the nodes and the antinodes, and the other definitions you learned, the overtones and the other frequencies in stationary waves. So those will be the topics that I will discuss in this video as well. So I hope that you have a further understanding about these waveforms before beginning this video. Alright. So as I mentioned you, resonance tube can be both act as a closed tube or an open tube. So you can take a closed tube and you can do the resonance experiment, as well as you can take an open tube and do the experiment. So I'll do both experiments in this video. So when doing the experiment with a closed tube, what you do is that you take a beaker like this. Now focus to this diagram here. You take a beaker like this, you fill it with water. So it's better if you put some cotton or sand first and then fill it with water. I'll explain why. So then what you do is that you take an open-end pipe. Although we are measuring or we are observing the characteristics of a closed-ended pipe, we take an open-ended pipe and we immerse this in water, or we drown in water, so that this is drowned now. So when we take a simple tuning fork and make it vibrate this air column near this open end, the air column is this near this open end vibrates. So there will be a stationary wave formed here. So the interface between the air column and this water, this surface, is actually now acting as the closed end for this open tube. Now when we vibrate the air column using a tuning fork, stationary waves are formed here. So you know that in a closed tube, that at the closed end a node is formed, and at the open end an antinode is formed, right? An antinode is formed, so it will be something like this: stationary form, antinode, and a node here. So sometimes what actually happens is that water also carries sound. So sometimes these waveforms may extend like this. Although we consider this to be a closed end at this interface, these sound forms will extend further into the water, and at this surface, if you don't have this cotton, wool or sand or any other obstacle here, at this surface it may reflect back here. So what you do actually is that you hear using your ear. So when you hear using your ear, what actually happens is that if these waves are reflecting back, you will not get the required value for the wavelength, and hence you cannot calculate the accurate speed of sound in air and the other stuff that we are measuring here. So what you do to prevent these reflections is that you put some cotton wool or sand here. So when a stationary wave is formed here, it will go down like this, and at least almost of the wave will be distracted here, so that the reflection is so small that we can hardly hear that. So you can get a pure stationary wave, pure sound stationary wave using this technique. So what you do, as explained, is that our objective is to find the length of the resonance tube at which resonance occurs. So you know that for resonance to occur, the frequency of this tuning fork should match with the natural frequency that is building up inside this open end. So we use the same setup here. So what you do is that if the frequency at which the tuning fork is oscillating is F, so it's always better in this slide, let me explain you. It's always better now these two ends of the tuning fork to be in line with the median column, or the distance, actually the red center. Now actually this, although I draw this in 2 dimensions, this is a 3-dimensional tube, a cylindrical tube. So the axis that goes through the center of this hollow tube to be in the same plane, or to be concentric actually, or to be with the same linear, with the same line as the ends of the tuning fork. So if you draw a line so that the line just merely touches the ends of the tuning fork, the line, when it is extended, it should go through the center of this tube. It's better if you do that, but it's not important, but you can get the best or a more accurate measurement using such a method. So what you do is that if you consider the tuning fork to be oscillating with a frequency of F, and the minimum length of the resonance tube at the time of resonance is L, right? At the time of resonance is L, the end correction is E, so you can measure the end correction easily. You can measure the end correction, and the wavelength of the wave formed due to the oscillation of air, you can say, now this is 1/4 of a wavelength, so this is an antinode, this is a node. You know that the distance in a stationary wave, the distance between an antinode and the node is 1/4 of its wavelength. So lambda by 4, lambda is the wavelength, is equal to L plus E. So lambda, when you multiply both sides by 4, or when you cross multiply here, you can say lambda is equal to 4 times L plus E. However, you know that V equals F lambda. V is the speed of sound. We can take V to be the speed of sound in air, F to be the frequency or the resonance frequency, and lambda to be the wavelength. So V equals F lambda. So V is equal to F times, now lambda is 4 times L plus E, so V equals F times L plus E. So in order to do an experiment, what we do, as in the case of other experiments, we draw a graph. To draw a graph, we have to have, whether it's a quadratic or a linear or a constant graph or even cubic graphs, you have to have some independent variable and a dependent variable. So what we do here is that we change the length, we'll change the frequency, of the tuning fork. We can do that by changing number of tuning forks. Say one tuning fork has a frequency of 256 Hertz, another 262 Hertz. Likewise, you can change, either increase or decrease the frequency. I'll explain about the sequence of frequency that you have to use here. So for now, think that you are either increasing or decreasing the frequency, and you change the length so that resonance occurs at some length. So the independent variable for this experiment will be the frequency of the tuning fork, and the dependent variable will be the resonance length. So when you isolate L here, L is equal to V by 4 times F minus E. So this is in the form of Y equals mx minus C. So this is a linear graph, linear expression, and the gradient M is equal to now V by 4, and intercept C is equal to minus E. So we can find the end correction of the tube and the speed of sound in air. So let's examine as to how. So as the first step of doing this experiment, what we do is that we set up the apparatus as shown. So this is the apparatus. This is the apparatus. So we set up the apparatus means we take a beaker here, we fill it with water, and if it's better if you fill it with cotton wool or sand first and then fill water. You fill it with water and you submerge here. You immerse this tube, this cylindrical tube, into water to some distance, and you, at the second step, what you do is that you take the tuning fork and that oscillated with the highest frequency and oscillate it, right? So I will explain as to why you take first the tuning fork with the highest frequency. Then you gradually lift the tube until a high sound is heard. So high sound is the moment that the resonance occurs. So this is the first resonance of this experiment. You measure the length at that instance from the upper level of water to the open end of the tube, and you verify that this length is the least length at which first resonance occurs. So that's actually step 5 is one of the most important steps in this experiment. Step 5 can be done by examining by lowering the tube and observing whether another high sound or another resonance can be heard at some length. You can decrease the length of the tube, right? You can do this here. You can decrease the length of this tube and find out whether at another length another loud sound or resonance is heard. If it is not heard, you can verify that the sound that you heard first is the first resonance and the length you took is the first length of that first resonance. So that is about taking the measurement from with the implementation or with the highest frequency, tuning fork with the highest frequency. Then you repeat this experiment, you record the resonance lengths for different tuning forks, you change the frequency of tuning forks, and when selecting tuning forks, it should be noted that they should be selected on the sequence of decreasing order of the frequencies, not in the increasing order. So say 512, 480, like that. I don't know the exact, I can't remember the exact value of these tuning forks, but say from 512 to 256, you decrease the frequency of tuning fork. So for the first time, first instance, or initially you are using a tuning fork with the highest frequency, say 512, and you decrease, and after 6 or 7 steps you are using the tuning fork available to you with the least frequency, that is vibrating with the least frequency, and you measure the length. You measure the length for those frequencies. You know the frequencies, so you can measure the lengths, and you draw a graph. Furthermore, you have to measure the thermometer. You take the room temperature using the thermometer as well, because the value of speed of sound changes with temperature. So you know that from the theory that you learned under waves, that when the temperature increases, the velocity of sound increases. So the temperature is also an important, although that is not in the equation that we are using to draw the graph, or using the equation that we use to identify the behavior. The temperature is also a key factor when determining the speed of sound, because temperature, the speed of sound in air you measure is at that temperature. If you want to measure the speed of sound in air for another temperature, say you are doing the experiment at 30 degrees Celsius or 303 Kelvin, but you want to measure the speed of sound in air at 27 degrees Celsius or 300 Kelvin, you can use the relationship between the speed of the sound in air and the temperature and find that relationship. So you have to find the temperature as well. So another important factor when doing this experiment is that when the air inside the tube is saturated after doing the experiment for some time, because now you know that now this is a tube, a metallic tube you use. So what you do is that after some time, water vapor may be formed due to vaporization. So after some time, you are doing this experiment for some time, say after 1 or 2 minutes, it will not be so saturated, but after some time, this water vapor inside the air inside this tube will be saturated by water. So thus this observed speed of sound in air is larger than the expected value at that temperature. You can't actually avoid that, because you can normally, we don't do the experiment with low vaporizing liquid. You can take some liquids with high vaporizing temperatures, high boiling points, but we normally take water for that. So we cannot remove this. Unlike the case of reflecting the sound waves, we cannot actually minimize this effect. So that's actually an error when you are doing the experiment. Now, having done the experiment, having explained the experiment for the closed tube, now let's consider as to how we can continue the experiment using an open tube. Now it's the same experiment, but if you are using an open tube, both ends should be open. So what you do here is that, unlike in the case of a closed tube in which you immerse the tube in water, what you do is that we do this experiment completely in air. We don't immerse either in water or any other liquid or any other solid. We completely do this experiment in air. So what you do is that, now you know that the waveform, when the stationary waveform that it will be formed inside an open tube will be as follows. You can see, and at both ends you can see antinodes here. So these are E means the end correction, and at the center you can see the node, right? So this is about the general form of the wave pattern that you will see inside an open tube. So what you do here, now if you do this experiment, now you know that you keep the tuning fork, so you do the same experiment for the open tube as well. So what you do here is that you change the frequency for the tuning fork, so that the value of f changes. You take the same relationship between the length of the tube and the frequency of the tuning fork, but you can change easily the value of the tuning fork, the frequency of the tuning fork. But unlike in the case of closed end, the experiment with a closed tube, you cannot now change the distance, because now this tube is fixed here, right? This is a fixed tube, so you cannot change the distance. So what you do is that you take a step like this. You take two tubes. Now both these tubes make an open tube, because at both ends these ends are open, so these two tubes make open. So you merge these two tubes. You don't weld these two tubes so that it is solidly merged. You just merge it. You just take it and you just put it inside here, right? So what you actually do is that you take two tubes, and you can keep this, you can pull this tube 2 inside tube 1, right? Tube 1 like this, and you can change the length. So length is this distance from this end of the tube 1 to this end of tube 2. So when you increase or decrease so the length of this tube by pulling the tube 2 inside tube 1 this way or this way, you can change the length. So that is the technique that we use here. So as in the case of the closed tube, we'll first of all, before doing the experiment, we'll derive a relationship between the speed of sound in air, the wavelength, and the frequency. So you know that since this is the waveform that you will be expecting, now you know that the distance in a stationary wave, the distance between two antinodes is half the wavelength, or lambda by 2, lambda being the wavelength. So that will be equal to the length of the tube L plus 2e. Now you have to take 2 times e, because the end correction will be shown at both ends. So the total length of the tube is now e plus L plus e, or L plus 2e. So lambda by 2 will be equal to L plus 2e, and also we know that v equals f lambda, so lambda equals v by f. So L plus 2e is equal to v by 2f, right? V by 2f. So what actually happens is that finally we can solve it, so that L equals v by 2 times 1 upon f minus 2e, right? So what you do here What we do here is that we change. So this is in the form of y equals mx minus c, where the gradient is v by 2 and the intercept is minus 2e. So the method that we undergo here is that we can arrange. Now we do an experiment that is very similar to that what we did for the closed tube. We take the two tubes, we arrange them, we keep a tuning fork perpendicular to the open end, so that actually the ends of the tuning fork and the center of this tube is linear. So it's always better to do that. And you change the tube until the high sound is heard, and that is the first instance at which resonance occurs. And as in the case of an open tube, you verify that by decreasing the length and verifying that there's no resonance lengths for that, the same resonance length that can be heard for the same tuning fork. So we verify this length to be the first resonance length, right? So it's always better if you make an analogy between the open end and the closed end tube when studying these two experiments. And we repeat the experiment for different tuning forks, and as in the case of the closed fork, you take tuning forks in the frequencies of decreasing order and you change the different lengths, right? You change the different lengths so that the resonance occurs, and you find the resonance lengths for those individual frequencies. Finally, you measure the temperature using the thermometer, because the speed of sound in air is the value that you get at that temperature. Using the gradient and the speed, using the gradient of the graph, you can find the speed of sound in air, and using the intercept of the graph, you can find the end correction of the tube. All right. So that's it about the resonance tube. So in this video, I explained to you about the concept of resonance, how resonance occurs, and two simple experiments, one using the open-end tube and the characteristics of the waveforms that you can see, about the behavior of waves, stationary waves inside a closed tube, and an open tube, about the concept of resonance. So in the next video, I'll be explaining you about a new concept on physics practicals. So thanks for watching this video, and see you then.